Without proper research and development, a lack of correct security implementation can turn an IoT object into security liability, not just for itself, but for the entire network and any connected devices. This demo was created to provide a more in-depth and better evaluation of the practical investigation that took place as part of this project. First, let's take a look at the circuit. The AutoCam runs using a Raspberry Pi 2 that is supplied power through a 5-volt micro USB port. This also provides power to the various GPIO hardware components that are connected to the Pi using a mini breadboard, which allows for easy configuration of the circuit by simply just taking these in and out. The only hardware component in this investigation that isn't connected directly to the breadboard is the Pi camera, which is connected using a ribbon connector that plugs straight into the Pi itself, as you can see down here. This breadboard circuit features two main GPIO components, a button and an LED. These were configured to accept various commands from the AutoCam's Python code, where to prevent the LED from burning out due to excess current, a resistor was used to limit the current. This would be ideal while developing a product that is designed for long-term use. So, for example, making sure the LED doesn't burn out over time due to continued use. Next, we will examine two Python files created in this project, with the first being the AutoCam's code, which is developed to handle secure communication using extended SMTP and MQTT protocols. When designing this code, the main critical processes were split into key functions that tackle a different task as part of the AutoCam's use as a smart doorbell. For example, an email class was created, which allows the code to create email objects that hold the captured doorbell image along with a message of notification for the user. Essentially, these functions wait for the button to be pressed to receive a signal that allows the Pi camera to take an image, which is then saved to a designated folder with an allocated timestamp. As I'm about to demonstrate by running the script, when the button is pressed, a message is displayed, confirming the capture of an image. Once saved, this image is taken along with the connected MQTT client and sent to the publish function. Here, the image data is read as bytes before being encoded with base64 to prevent the JSON messaging format from breaking. Once converted, the client then publishes this image to the MQTT cam photos topic to be received by any subscribed user. Once complete, the next step for the AutoCam is to send an email notification to users by creating an instance of the email class. This object is given values that are used to form the base of the email being sent out, which includes the recipient email ID, the email subject, and the content found within. These values, along with the captured image, are passed into the send email function, which uses the MIME library to attach the given values together. However, for the captured image to be accepted as part of the email, it must first be read as bytes to be converted into a MIME object that can be attached to the notification email. With the email formed, the AutoCam then sets up a new session, SMTP session with the Google Mail server, making sure to enable transport layer security on connection. Once connected, the AutoCam logs onto the server using a given unique passcode and initiates the connection using sesh.ehlo. Once acknowledged and the connection is confirmed, the email is sent to the recipients and the connection is closed to prevent errors. Here is a screenshot taken from the test email recipient confirming the delivery of the notification message. As you can see, the image is there attached along with the email as well. The next file we'll be examining was developed to receive published images that have been posted to the cam photos topic by the AutoCam using MQTT. This script functions so that whenever executed by a compatible device, the program listens out for newly published images to accept them into a queue so that they can be saved into the designated folder. Let's take a closer look at the code. The Paho MQTT library includes a client class that essentially allows the AutoCam to connect to an MQTT broker we'll be using to receive notification images from the AutoCam. While the Patlib library offers classes that allow the script to navigate the queues it will pass messages into. This script follows the same style as the first file for the AutoCam, where the key processes have been split into functions that can be called from within main with ease. When the onConnect function is called, the broker and port is passed in to attempt a connection to the MQTT broker. If successful, they receive a message saying, "Establish connection successfully." The next function, onMessage, is repeatedly called within the main function to receive any new messages published on the MQTT topic. As I'm about to show you, when the script is run, it begins listening for newly published notifications. Once received, it is saved to this folder path that we have declared up here. That concludes this demonstration. Hopefully you now have a clearer understanding of the practical investigation carried out as part of this project.